Hey everybody. There's one more thing I wanted to talk about in our little detour through basic physics before we jump back into astronomy and see how all of these concepts of physics work in stars and planets and galaxies and everything. And that is, I wanted to talk about matter. Uh, Matter is what? It's what things are made of, right? Matter is the nouns of physics. Matter is the nouns and energy is the verbs, right? Matter is what things are made of and energy is what makes things go. But I wanted to talk about what kinds of particles are we talking about and how do they work? Well, when we talk about matter in a chemistry class, say, then we probably talk about matter in terms of the periodic table. The periodic table organizes atoms by their chemical properties. Every hydrogen atom chemically reacts the same as every other hydrogen atom. Every helium atom chemically reacts the same as every other helium atom. So the periodic table is a way of organizing atoms according to their elements, according to their chemical reactions, their chemical behavior. And in chemistry, I guess you can make this diagram where all the boxes are the same size because every chemical is important in chemistry. But in astronomy, some chemicals are a little more important because they're more abundant in astronomical objects. Um, Here on Earth, the Earth is mostly made of iron, silicon, and oxygen, and a lot of other things like magnesium and carbon and nickel and things like that. But that's iron, oxygen, and silicon explain most of the Earth. In the sun, when you look at the absorption spectrum of the sun, you can tell that the sun is mostly 73.5% hydrogen. So the sun is mostly hydrogen, with also a lot of helium. Every other element of the periodic table is just 1.5% of the composition of the sun. There's a fair amount of carbon, oxygen, nitrogen, iron, other things in the sun, but the sun is overwhelmingly hydrogen and helium. And the sun is not peculiar in that respect. Most stars in the universe are mostly hydrogen with a lot of helium and just a little bit of everything else. So here's what the periodic table for an astronomer looks like. Right? The most important element in the universe is hydrogen because that's what most of everything is made of. And the second most abundant element is helium, and everything else, the entire rest of the periodic table, from lithium all the way down the periodic table, all the way to uranium, is just this tiny little trace elements in a universe that is overwhelmingly hydrogen and helium. So in astronomy, we lump all of these other little elements at the bottom of the periodic table, and we call them all metals. So what is the universe made of in astronomy? The universe is made of hydrogen, helium, and metals. And I put metals there in dubious quotation marks because in astronomy, that's what metals are to us. It's just anything that isn't hydrogen or helium. So we don't just mean, metals the way you would say metals in a chemistry class, right? In a chemistry class, metals are copper, gold, iron. But in astronomy, metals includes oxygen and carbon and nitrogen and everything else that's heavier than helium. And an atom is the smallest amount of something. An atom is the smallest unit of a substance, of a material, that you can have that still behaves like that metal or like that element. If you took a bar of iron and if you broke it in half, you'd have two smaller bars of iron. And if you took one of those smaller bars and broke it in half, you'd have an even smaller bar of iron. And if you just kept taking these small bars of iron and breaking them into smaller and smaller and smaller and smaller slices, you would have a smaller amount of iron, but it would still be iron. It would still behave. It would still chemically react and conduct electricity and all those other things like iron does. Until you finally get down to a single atom of iron. A single atom of iron will still act like iron, But it's if you break that atom into its subatomic particles, if you break that atom up into even smaller particles, then they don't behave like iron anymore. Then you're just looking at the individual subatomic particles. So if you take a single atom and zoom in on it, then what do you see? Well, you see the nucleus of the atom at the very center, and that nucleus is being surrounded by the electron cloud. And what's the nucleus made of? The nucleus is made of protons and neutrons. Protons and neutrons have way more mass than electrons do. So it is the supreme irony of the universe that we live in that when you look at atoms, all of the mass is concentrated at the very center. All of the mass is concentrated in the nucleus. But the size of an atom, the space that an atom takes up, is mostly the electron cloud made of electrons that don't have that much mass. And atomic nuclei are much, much smaller than the electron clouds are. So I put this illustration together to show you, to give you a sense of scale, that if you look at an atom, the atom itself would take up a football field, but most of that space is just the electron cloud. If the whole electron cloud were the size of a football field, then the nucleus would be the size of a single grain of sand sitting there in the middle of the field. And all of the mass of that atom is concentrated in that one grain of sand. So that atoms are mostly just made of empty space. Atoms are mostly the empty space in between the electrons of the electron cloud, but all of the mass is concentrated in that nucleus at the very, very center. So all of this about the structure of atoms was being figured out in the early 20th century. And by before that, around the time of the turn of the 20th century, physicists were feeling very proud of themselves. You know, they had figured out how gravity worked, they had figured out how electromagnetism worked, and they thought, at the time, that those were the only two fundamental forces in the universe. That every force in nature could be described either in terms of gravity, which comes from the mass of particles, or it can be explained in terms of the electromagnetic force, which is determined by the charge on particles. And so chemists and physicists were, slapping themselves on the back saying, well, we figured out everything. We've solved all the problems. We know how everything works. Everything in the universe is working, is being powered just by gravity and electricity. But then a few years later, they started realizing that, well, what is the nucleus of an atom made of? Well, the nucleus of an atom is made of protons and neutrons. Protons have positive charges. Neutrons have no charge. So, how are they sticking together? Because the electric force, if you set two positive charges next to each other, those two positive charges want to repel each other. The electric force wants them to fly apart. Neutrons feel no charge. They have no charge. Since neutrons have no charge, they don't feel the electric force. The electromagnetic force only works on charged particles. So the neutrons don't feel the electric force. The protons feel the electric force, and the electric force wants those protons to just fly apart. So how do these nuclei hold together? How do these nuclei stay stuck together when the electric force wants them to fly apart? And, the reasonable first guess that anybody would throw out is, oh, well, it must be gravity, right? Gravity wants to pull everything together, and so gravity must be stronger than the electric force, so that gravity is holding the nuclei together stronger than the electric force wants everything to fly apart. But then you do the math, and that's not so. The electric force between protons and neutrons, or between the protons specifically, the electric force is way stronger than the gravitational pull between them. Gravity is nowhere near strong enough to hold protons and neutrons together when the electric force wants them to just fly apart. So there must be a third force at play here. If you can't explain the nuclei of atoms in terms of gravity or electricity, there must be a third force of nature that is stronger than the electric force. And that this third force is gluing the protons and neutrons together, that there must be a force in between the protons and neutrons gluing them together stronger than the electric force wants to repel the protons. And that's how nuclei stay together. This force they've come to call the strong nuclear force. It's called the strong nuclear force because it exists in the nuclei of atoms, and it is stronger than electricity. And that's what holds the protons and neutrons together, is this strong force. So everything's solved, right? Now we can understand everything in nature in terms of gravity, electromagnetism, and the strong force. Well, not quite. There was, around this time, again, the 20s, the 30s, there was another phenomenon, radioactivity. Why does that happen? Why are some atoms radioactive? Why do they decay and break down and other atoms don't? Well, that radioactivity is happening in the nuclei of atoms also. And so, well, there must be a fourth force out there. There must be a fourth force that causes radioactivity because we can't explain radioactivity in terms of gravity, electromagnetism, or the strong force. And yet, this fourth force, it's happening inside nuclei. So it's a nuclear force, but it's not as strong as the strong force. So we'll call it the weak nuclear force. How does the weak nuclear force work? Well, think about it like this. I mean, this is my silly little cartoon here, but what am I trying to say with my silly little cartoon? What I'm trying to say is, when you pack protons and neutrons together in a nucleus is kind of like an apartment, where you've got these protons and neutrons, and these protons and neutrons are like roommates, right? You've got all of these roommates packed together in an apartment, and if you get the right mix of protons and neutrons, it's like having the right mix of roommates in your apartment. And as long as you've got the right mix of roommates in your apartment, everybody stays happy, the whole roommate situation is stable, and everybody holds together. But if you got too many particles, if you've got too many protons or too many neutrons, if you don't have the right mix of particles in your nucleus, it's kind of like having the wrong mix of too many roommates in too small of an apartment, and pretty soon they can't quite strike a good balance. The protons and the neutrons, they're not happy. They don't bind together under the strong force in a stable situation, right? Because with all these particles, you've got the electric force wants the protons to fly apart, and the strong force is trying to glue them all together stronger than electricity is working, but it's not working out. The strong force doesn't hold all these particles together stronger than the electric force wants to repel them. And so everybody's kind of unhappy, and all these particles are moving around and trying to bond and trying to push each other away and trying to stick together, and it's like having a bad situation of roommates where people are trying to be peaceful, but they just keep on fighting, and there's no balance of forces between you and your roommates, and pretty soon something's going to break down. Pretty soon something comes in and either makes the whole thing fly apart, or settles things down and makes peace. And the thing that settles this fight is the weak nuclear force. Because as these protons and neutrons are moving around and can't find a stable situation, sooner or later the weak nuclear force comes in, and the weak nuclear force, in this case, with this nucleus, what can happen is the weak nuclear force comes in and says, "Hey, neutron, why don't you turn into a proton?" Because by changing by changing that neutron into a proton, now there's a good balance. Now there's a nice stable balance between protons and neutrons. They can settle into a happy, stable situation. The strong force is now is back to being stronger than the electric force, and this nucleus has gone back to being stable. But what happened? What happened was, in changing that neutron into a proton, you've created a positive charge, right? This was a neutron, and now it's a proton. It went from having no charge to having a positive charge. Well, electric charges can't just spring up out of nowhere. And so by changing this neutron into a proton, you also, that proton ends up spitting out an electron. And that electron carries away a negative charge, and that electron shoots out of the atom, and that's your radioactivity. That's your radioactive particle that comes flying out of the nucleus. Radioactivity happens, and radioactive particles get emitted as a way for the weak force to take unstable nuclei and turn them into more stable nuclei. So the weak force, if my example here seems cartoonish and dumb, it's because it's kind of cartoonish and kind of dumb. I'm definitely simplifying things significantly, because the weak force is not really a force in the way that gravity or electricity or magnetism are. The weak force is a force between particles that communicates what their identity is. Right? A proton is a proton because of the way it interacts with the weak force. An electron is an electron because of the way it interacts with the weak force. And when the weak force steps in and pokes something or pushes it or adjusts it, what the weak force ends up adjusting is the identity. It can change a neutron into a proton and an electron, causing radioactivity and stabilizing unstable nuclei. So those are the two new forces that people have been working on and still are working on, trying to figure out exactly how they work for the rest of the 20th and now into the 21st century. The strong force and the weak force, though, they're nuclear forces. They only happen, the strong force and the weak force only work over very short distances, which is why they only happen inside the nucleus of an atom. Once you get outside the nucleus of an atom, those forces become effectively zero strength, and so outside of a nucleus, then the only forces that really matter are electromagnetism and gravity. So when you put all this together, this is what powers the universe. There are four fundamental forces in nature. There's gravity, based on mass. There's electromagnetism, based on charge. And there's the strong and weak nuclear forces that glue together or fly apart protons and neutrons inside the nucleus of atoms. And every other force of nature, everything that happens in chemistry, biology, physics, everything is just, every action in the universe, every energy in the universe is just an example of these four fundamental phenomena. The reason why I wanted to talk about this right now is because we're going to see these forces in action inside of stars. And so in order to understand why stars do what they do and understand how stars work, we need to understand these four forces. So we'll be seeing these in action very shortly. For now, let's instead of talking about forces, let's talk about matter. Let's talk about what matter is made of. Um, a minute ago, I said atoms are made of protons, neutrons, and electrons, and that's true. But if you zoom in and look at a proton, it turns out that protons and neutrons are made of even smaller particles that are called quarks. And there are, for our story here, there are two kinds of quarks, up quarks and down quarks. And if you have two up quarks and a down quark, two up quarks and a down quark combine together to make protons. Two down quarks and an up quark make neutrons. So both protons and neutrons are made of these up and down quarks. And what holds these quarks together in protons and neutrons? That's also the strong force. So now, what are the fundamental particles that make up matter? Well, you've got up and down quarks that make up protons and neutrons, and then you've got electrons. And that's almost the whole story. Except, as particle physics went on over the 20th century, physicists discovered that there are even more particles that are like up quarks, down quarks, and electrons. There are also these neutrinos. What are neutrinos? Well, neutrinos are very small, very low mass particles, kind of like electrons, except they're much lower mass than electrons, and an electron already doesn't have a lot of mass, but neutrinos have even less mass than an electron, and they have no charge. Neutrinos are neutrally charged, which is why they're called neutrinos. So for our purposes in this class, we're mostly interested in this first column here, what particle physicists call the first generation of matter. Up and down quarks make protons and neutrons. You throw on some electrons orbiting around those protons and neutrons, and you've got atoms, and from atoms you can make molecules and everything else in the universe. The second and third generations of matter are basically just higher mass cousins of the first generation. So charm quarks and strange quarks are like up and down quarks, only higher mass. Top quarks and bottom quarks are like up and down quarks, but they're even higher mass, even higher than the charm and the strange quarks. Electrons have higher mass cousins too. They're called muons and tauons, or tau particles in this chart. And then neutrinos have higher mass cousins too. So the second and third generations are just higher mass versions of the first generation. And because the second and third generations are higher mass, it takes more energy to make them. The second and third generations of matter don't really happen in nature. The only reason that we find second and third generation matter is because we manufacture it. They're man-made in particle accelerators. Because in a particle accelerator, you've got an incredibly hot, high-energy environment where you can manufacture these higher mass cousins, but they're not stable. Second and third generation particles are very unstable, and they break down and they turn into first generation particles in very short order. So what you find in nature, what you find in planets and stars and galaxies, is just first generation stuff. And then these particles on the right-hand side, they're called the force carriers, because these are the particles that carry the forces. So photons are particles of electric and magnetic fields. Gluons are the particles that carry the strong force. And I kid you not, they're called gluons because they're what glue protons and neutrons together in the nucleus. And then the W and Z bosons are the particles that carry the weak force. Is there a particle that carries gravity? Right? The photons are particles that carry electromagnetism, strong force, and the weak force. What about gravity? Is there a particle that carries gravity? That is a question that still hasn't been answered. Some particle physicists can do some math and they can say, oh, yes, yes, there must be a graviton particle. There must be a particle that carries gravity. No one's ever seen one, though. So, are particle physicists right? Is there a particle that carries the gravitational force? Or are they just doing some fun math, but they're not actually describing something real in nature? That is a question that has not yet been answered, but people are working on that one. So that's normal matter, right? Up quarks, down quarks, and electrons are what combine together to make normal matter. A few years later, some of these particle physicists also discovered that, well, it turns out there's even more particles in the universe because every particle in nature also has an antimatter cousin. Antimatter particles are basically the mirror image of normal matter particles. Antimatter particles have the same mass as their normal matter cousins, they just have the opposite charge. So there is an anti-electron. Usually anti-electrons are just called positrons. But a positron, or an anti-electron, is a particle that has the same mass as an electron. It just has a positive charge instead of a negative charge. Antiprotons have the same mass as protons. They just have a negative charge instead of the proton's positive charge. So it turns out that every kind of particle, every quark, every lepton, protons, neutrons, electrons, they all have antimatter cousins. And when matter and antimatter meet up, they destroy each other. That when you have an electron and an anti-electron, or a positron, right? When an electron and a positron collide, they absolutely destroy each other. They convert from particles and they annihilate each other and they turn into a flash of photons. And after those photons are gone, there's no matter left. The same thing happens with protons and antiprotons. When protons and antiprotons collide, they absolutely destroy each other and they turn into a spray of light. Essentially, what happens with matter-antimatter annihilation is that mass turns into energy. Particles, like electrons and positrons, get destroyed and turned into energy. How can that be? How can you have particles turn into just energy, light? Well, it turns out that one of the things that Einstein discovered with his theory of relativity is that mass is just another form of energy. That's what E equals mc squared means, Einstein's famous equation. What this equation means is that the energy that is contained in mass is equal to the mass of that particle times the speed of light squared, right? The speed of light is symbolized with a c. And so energy and mass are interconvertible. You can convert mass into energy, or you can convert energy into mass. You can convert particles into photons. You can convert mass into energy because they're all the same thing. What I started saying at the very beginning of this talk about how physics is the story of matter and energy, and that matter is what makes things up and energy is what makes things go. Well, what Einstein discovered about 100 years ago is that it's all the same thing. That just like you can find energy as kinetic energy, you can find energy as thermal energy or potential energy, you can also find mass energy. That mass is just another way that energy happens in the universe. And that you can take matter, you can take mass, like a proton and an antiproton, and you can completely convert them into energy, and those become gamma rays. They become high energy photons that shoot out from where the matter and the antimatter annihilated each other. And it turns out that mass contains a heck of a lot of energy, because if you take the mass of a particle, if you take the mass of a proton, not a lot of mass, one proton doesn't have a lot of mass, but then you take that mass and you multiply by the speed of light squared. Right? The speed of light is a big number. The speed of light squared is a huge number. So even if you take a small amount of mass and you multiply it by the speed of light squared, that mass turns into a huge amount of energy. And this is the energy that powers stars and nuclear reactors. So if we can understand, okay, what particles are made of and how particles work, then we can get a handle on how particles can turn into energy, because that's the energy. What you're looking at right there, that E in E equals mc squared, is the energy that becomes the luminosity of stars. So that's the next stop on our journey. Now that we've got a basic handle on energy and matter and gravity and motion and all of these basic concepts of physics that we've been talking about, now we're ready to jump back inside of a star and say, how are these forces all conspiring together to explain the stars that we see in the universe, and the planets, and the nebula, and the galaxies, and everything? I hope this has made some sense. If you've got some questions, please bring them into class the next time we meet up, and we can hopefully clarify any parts where you're stuck on all of these videos. Until then, have a great day.